Welcome to Spring LIB.
Once again, welcome to a new problem. This time we'll still have a slit. This is a double slit. So double slit means that we have two openings, if you want to think of it that way. It's still diffraction. We are dealing with diffraction right here. And if you have two slits, there's obviously light that's going to be going through. Initially, the light is perpendicular, but then spreads out under diffraction and ends up producing bright fringes, if you want to call them that. So if this happens to be a screen, if this is a screen, we're going to end up with bright fringes on the screen, and in this case, we have 8 of them, 8 fringes. So that's what we're looking at, and that's the diffraction that we're dealing with. So our goal in this particular problem is to see that, for example, there's a gap. There's a gap right here. This is a gap. That's the distance between two openings. That's D, and then on the other side we have the distance between the actual opening. So the width. This is W. So that's the width. We're calling it W. And this is the gap. D is the gap between two successive openings. You want to see that. So if we look at the problem and we have all these bright fringes, we have 8 of them. The goal of the problem is to determine the ratio of D versus W. So that's the goal of the problem. We want to determine the ratio of D versus W, assuming that the minima connects or overlaps. The minima connects or overlaps to the maxima, to the interference maxima. We want to see that. So that's what we're given in this particular problem. The first thing we want to do is we want to go ahead and see that D, we know that D sine theta equals to m lambda, and that's for double slit interference. So that's the condition we're dealing with. And as you can see, D was the gap between the two openings, and W was the width. We know that M is the order. M is the order, and lambda, this is lambda. Lambda is the wavelength. That's the wavelength. That's our lambda. Theta is the angle of diffraction. Theta is our angle of diffraction. And so if we look at this problem, the distance, if this is our central max, that's our central max. The distance of the central max is y. So y is the distance of the central max that we're dealing with. And then also, we do have another relationship. We know that y is m lambda, capital D, over small d. Remember, capital D is a distance, and it's a special distance from the acromen to the center of the two slits, to the center of the two slits. So remember these two slits, the center is right there. Okay, so that's what we're dealing with. So for single diffraction, this center is a dark or bright spot. Now, in the problem, there's an understanding that we have 8 bright fringes. We have 8 bright fringes within the first envelope. And so the order for the dark fringes is 1, and the for double interference, this is for single interference. For double interference, the order is 8 plus 1, which is 9. So we can go ahead and work through the equation. Y equals to m lambda capital D over small d. And so we can multiply both sides by D and then divide both sides by Y. And so D equals to, these two cancel out, m lambda capital D all over Y. That's what we're dealing with. And remember, m was 9, so we can do a substitution. We have 9 lambda capital D over Y. For the slit width, we know that A equals to m lambda over D over Y. Sorry, m lambda over Y. For the single slit, m equals to 1, and so we have A equals to lambda D over Y. Remember, this becomes 1, so we do the replacement. And so now we have two equations. We have, this is our second equation, and this is our first equation right here. This is equation number 1. This is the same equation. Of course, we introduced the 9 as an order, so we're going to divide those two equations, and we end up having D over A is the same as 9 lambda capital D over Y, and then 1 lambda capital D over Y. So this gives us 9, and so the ratio of the slit separation is going to be 9. That's the ratio of the slit separation. So, once again, just highlights to the requirements of the problem is the fact that it's a two-slit interference. It's a two-slit interference. As you can see, we have two slits, the first one and the second one. And there are 8 bright fringes, 8 bright fringes, and the minima connects or overlaps the interference maxima in this instance. So we want to find the ratio of these two openings. We're dealing with two openings right here. There's the gap, and then there's the width. Those are the two openings we're looking at in this particular problem. And so we start by using the condition for double interference, D, this one right here, D sine theta equals to m lambda. So we go ahead and see that D is separation between two openings. That's D lambda is a wavelength, and theta is the angle, diffraction angle. So we know that y is m lambda capital D over small d, where y is the distance of the central max. So think of it this way: if you have openings right there, and this is your central max, so you have that distance, and lambda is the wavelength, m is the order, d is the separation. This is d right here. That's the separation between two openings. So the center point of the two slits is right here. That's the center point of the two slits. So we're getting comfortable with the requirements of the problem. We're getting comfortable with the requirements of the problem, and now we have two equations. We have the initial equation, d sine theta equals to lambda, d sine theta equals to lambda. And so this capital D, this one right here, is the distance from the center of the interference up until the gap. And if I had some light going on like this, if I have interference going on like that, then obviously the distance between the fringe right there and the center is going to be my y. So that's this y you're dealing with 8 bright fringes. So in terms of order in a single slit, the order is 1, but in double interference, the order is 9. So now we have these two equations that we're dealing with. The first one will require that we solve for D, which is the gap between two slits. And so we reorganize this particular problem, and we cancel the D's on both sides. As you can see, this is canceled out, and this is canceled out. And also the y's are canceled out. So you solve for D. That's the first equation that we're dealing with. And we know that m equals to 9, so we plug in. And then in the second equation, we know that m equals to 1, and that gives us the width that we're dealing with for a single slit. And then we get the ratios. D over A is the same as 9 if you simplify it. So hope you enjoy the problem. Feel free to send any questions or comments, and have a wonderful day.